Most people still picture Pluto the way they learnt it in school. A tiny snowball at the end of a diagram. Harmless, cute, familiar. That picture is wrong. When NASA's New Horizons spacecraft reached Pluto in 2015, it found a world no one predicted. Glaciers of nitrogen ice larger than Texas, slowly churning from heat escaping the interior. Mountains of frozen water standing as tall as the Rockies. Skyscraper-sized blades of methane stretching toward a sun so distant it looks like just another star. Ice volcanoes that may have erupted within the last few million years, and an atmosphere unlike anything else in the solar system, one that is literally bleeding onto its own moon. Pluto is not what you think it is. It is far stranger and far more disturbing than you were ever told. If this kind of deep science storytelling is what you come here for, please take a moment to like this video and subscribe to the channel. It genuinely helps more than you might think, and it is the reason we are able to keep making content like this. Are you comfortable? Now, let's begin. There is a version of Pluto that lives inside almost every person who went to school in the 20th century. It sits at the end of a diagram. It is the smallest circle on the poster. It is painted a vague brownish grey and placed after Neptune, usually with a little dotted line showing its tilted orbit. Maybe there is an arrow pointing to it that says Pluto in a child's handwriting. Maybe there is a cartoon dog standing next to it, because for most people the Disney character and the planet are stored in the same drawer of the brain, and neither one feels particularly serious. That version of Pluto is one of the most successful lies in popular science. Not a deliberate lie. Nobody set out to deceive anyone. But the result is the same. Billions of people carry in their heads a picture of Pluto that has almost nothing to do with the actual world. They think of it as small, simple, frozen, solid, and essentially dead. A cosmic afterthought. The runt of the solar system family portrait, placed at the far end of the lineup like a younger sibling nobody expected. Cute, harmless, vaguely sentimental. Something you might feel sorry for, especially after 2006, when astronomers voted to strip it of its planet status and the internet erupted in sympathy as if a beloved pet had been sent away. And for decades, that sentimental picture was a reasonable one to carry. Because we had almost no data. Pluto was discovered in 1930 by a young astronomer named Clyde Tombaugh, working at the Lowell Observatory in Flagstaff, Arizona. He found it by comparing photographic plates of the night sky taken on different nights, looking for a tiny dot that moved against the fixed background of stars. It took months of painstaking work. When he found it, the dot was so faint and so distant that virtually nothing could be determined about it other than the shape of its orbit. It was out there. It was far. It was cold. Beyond that, science had almost nothing to say. For the next 85 years, Pluto remained a point of light in even the most powerful telescopes. The best images the Hubble Space Telescope could manage showed a blurry smudge, a few pixels wide, with hints of light and dark patches but no detail, no surface features, no geology, no terrain. A world defined not by what it was, but by what people imagined it to be. And into that vacuum of knowledge, the human imagination poured a story, a small, frozen world at the end of the road, quiet, lonely, endearing in its remoteness, a place you could almost feel sorry for. The kind of place that fit neatly into a mnemonic device about the order of the planets and otherwise asked absolutely nothing of you. That story held for 85 years. Then, in July of 2015, a spacecraft the size of a grand piano arrived at Pluto after traveling more than 3 billion miles across 9.5 years of empty space. And the story collapsed. But before we talk about what that spacecraft found, we need to talk about what it means to be where Pluto is. Because the distance alone changes everything. And most people have never actually been asked to think carefully about what that distance feels like. Pluto orbits the Sun at an average distance of roughly 3.7 billion miles. That number does not communicate anything useful to a human brain. It is too large. It is the kind of number that slides off the surface of comprehension the way water slides off glass. You read it. You nod. You feel nothing. So let us try to make it real. Light is the fastest thing in the universe. Nothing moves faster. A beam of light travels at approximately 186,000 miles every single second. At that speed, light crosses the distance between the Earth and the Moon in just over 1 second. It reaches the Sun from Earth in about 8 minutes. That same beam of light, continuing outward past the inner planets and into the deeper solar system, passes Mars in roughly 12 minutes. It reaches Jupiter in about 43 minutes, Saturn in around 79 minutes, and then the distances begin to stretch in a way that feels qualitatively different from anything closer in. Uranus is about 2 hours and 40 minutes away at the speed of light. Neptune is just over 4 hours, and Pluto, at its average distance, is 5.5 hours away. 5.5 hours for light to travel from the Sun to Pluto. That means the sunlight falling on Pluto's surface right now left the Sun before you started watching this video. It was already crossing the void before you sat down. It has been traveling since before lunch. At the speed of light, the fastest speed the universe allows. Now think about what that distance means for communication. If you were standing on Pluto and you sent a radio message home to Earth, that message would travel at the speed of light. It would take between 4.5 and 6.5 hours to arrive, depending on where Pluto and Earth are in their respective orbits. Your family would not receive your words for the better part of a working day. And then their reply would take the same amount of time to travel back. A single exchange of conversation, one sentence, and one response would consume 10 to 13 hours. You would be, in the most literal and physically enforced sense possible, profoundly and functionally alone, not metaphorically alone. Not alone in the way a person feels in a remote cabin where a phone still works and a helicopter can still reach you. Alone in a way that cannot be overcome by any technology that obeys the laws of physics. The speed of light is a wall. It is the hardest wall in the universe. And at Pluto's distance, that wall turns human connection into a delayed, ghostly, almost ceremonial act. You could send your words into the dark and then sit for half a day, waiting, hoping, knowing that the reply was already on its way before you could even be certain the message was received. Now think about what that distance means for the Sun. From Earth, the Sun dominates the sky. It is blinding. It fills the world with warmth and light. It defines the difference between day and night. It is the engine behind weather, behind photosynthesis, behind the entire energy budget of the biosphere. It is so central to the human experience that virtually every ancient civilization built its religion around it. From Pluto, the Sun is a bright dot, not a disk, a point of light. Brilliant compared to the surrounding stars. Yes, roughly 250 times brighter than the full moon appears from Earth. You could still read by it, you could still see. But it is small enough that you could block it out with the tip of your little finger held at arm's length. You could cover it with the head of a pin. The amount of sunlight reaching Pluto's surface is roughly 1/1500th of what reaches Earth. That is not dim in the way that a cloudy afternoon is dim. It is dim in the way that deep twilight is dim. Stand on Pluto at high noon, and the illumination around you would be comparable to the last fading minutes after sunset on a clear evening on Earth. The sky would not be bright, the ground would not be warm. There would be no heat in the light at all. You would see, but you would see the way you see, in those final quiet moments before full darkness closes in on a summer night. A pale, grey, colourless glow that never strengthens, that never becomes day. That simply is what noon looks like when you are 3.7 billion miles from your star. And that dim grey light is the maximum. Pluto's orbit is not circular. It is highly elliptical, swinging from roughly 2.7 billion miles from the Sun at its closest approach to 4.6 billion miles at its farthest. That range changes the amount of sunlight Pluto receives by a factor of nearly 3 across the course of its orbit. And Pluto's orbital period is 248 Earth years. A single year on Pluto is longer than the entire history of the United States. That means Pluto's seasons, such as they are, unfold across timescales longer than most human civilizations have lasted. There are regions of Pluto that spend decades in continuous darkness during their polar winter. Not hours of darkness, not weeks, decades. An entire human lifespan could begin and end in old age before sunrise arrives at certain latitudes on Pluto. Let that settle for a moment. There are places on this world where the sun does not rise for longer than a person can live. The surface temperature on Pluto averages roughly -387 degrees Fahrenheit. That is approximately -232 degrees Celsius. It is roughly 40 degrees above absolute zero, the theoretical floor of the temperature scale, the point at which molecular motion effectively ceases. At these temperatures, the air you are breathing right now would not exist as air. Nitrogen, the gas that makes up 78% of Earth's atmosphere, freezes solid at these temperatures. It becomes ice. It becomes the ground. The surface you would walk on at Pluto is not rock in the way you understand rock. It is frozen nitrogen, frozen methane, frozen carbon monoxide, lying in sheets and drifts and glacial plains atop a bedrock of water ice that at these temperatures is as hard and as rigid as granite on Earth. Water ice at 40 degrees above absolute zero does not melt. It does not deform easily. It is structural. It is what mountains are made of on Pluto. At these temperatures, a steel wrench would become so brittle it could snap in your hand. Rubber would shatter like ceramic. The lubricants in any mechanical device would freeze solid. The chemistry of everyday materials ceases to apply. Nothing about the physical environment of Pluto resembles anything in human experience. The cold is not merely extreme. It is a fundamentally different category of physical reality, one in which the ordinary assumptions your body and your brain and your technology were built around simply do not hold. And yet, despite all of this, for most of the 20th century, the scientific expectation was that Pluto would be simple. Cold, yes. Far, yes. But geologically dead. A frozen marble floating in the dark with a few craters scattered across an unchanging surface. A world that shut down billions of years ago and has been sitting in silence ever since. The reasoning was sound. Small, cold bodies in the outer solar system are expected to lack the internal heat necessary to drive geological processes. Earth has volcanoes and earthquakes and drifting continents because its interior is still hot, powered by radioactive decay and by the residual energy of the planet's violent formation 4.5 billion years ago. Mars, smaller and farther from the Sun, lost most of its internal heat long ago. Its great volcanoes are extinct. Its surface is largely a frozen record of ancient catastrophes. Pluto is far smaller than Mars, roughly 1/50th of Mars's mass, far colder, far more remote. The logic was direct and seemed impossible to challenge. Whatever geological processes might have shaped Pluto's surface early in its history should have shut down billions of years ago. There should be nothing happening there now. The surface should be a frozen record of the ancient solar system and nothing more. That logic was wrong. NASA launched the New Horizons spacecraft on January 19, 2006. It left Earth atop an Atlas V rocket and entered interplanetary space as one of the fastest objects ever launched from this planet, departing at roughly 36,000 miles per hour. Even at that speed, faster than any bullet, faster than any aircraft, faster than any crewed vehicle in history, it took 9.5 years to reach Pluto. 9.5 years of crossing the void. 9.5 years of coasting through the silence between worlds, past Jupiter in 2007, where it picked up a gravitational slingshot that added another 9,000 miles per hour to its velocity, then outward through a region of the solar system where the sun grows dimmer behind you with every passing month, and the emptiness ahead stretches beyond imagination. New Horizons arrived at Pluto on July 14th, 2015. The encounter lasted only hours. The spacecraft could not slow down and enter orbit. It did not carry enough propellant. The mass of the extra fuel would have required a larger and more expensive rocket, or it would have delayed the mission by years. So, New Horizons was designed as a flyby mission. A single screaming pass at roughly 31,000 miles per hour, during which every instrument on board fired continuously, capturing as much data as physically possible in the narrow window when Pluto filled the cameras. The closest approach brought New Horizons within about 7,750 miles of Pluto's surface. Then the spacecraft hurtled past, and Pluto began to recede behind it, and the long process of transmitting the data home began. Because of the staggering distance, the data trickled back slowly. The communication link between New Horizons and Earth operates at a bandwidth roughly comparable to a 1990s dial-up internet connection. Each image, each spectrum, each particle count crept home across 3 billion miles of vacuum at the speed of light, collected by the giant dish antennas of NASA's Deep Space Network in California, Australia, and Spain. It took over 15 months for the full dataset to arrive on Earth. Scientists spent years analyzing what came back, and what came back shattered the model entirely. The first high-resolution image of Pluto showed a heart. A massive, bright, heart-shaped region dominating one hemisphere of the world, so vivid and so geometrically crisp that it looked almost intentional. Scientists named it Tombaugh Regio, after Clyde Tombaugh, the man who had discovered Pluto 85 years earlier. The heart was immediately iconic. It appeared on magazine covers around the world. It trended across social media for weeks. It became the defining symbol of Pluto's enduring charm, the cute little world at the edge of the solar system with its heart on its sleeve. But the charm lasted only as long as it took to look closer. The western half of the heart is a basin called Sputnik Planitia. It is roughly the size of Texas and Oklahoma combined, approximately 1,000 kilometers across. It is filled with nitrogen ice, not a thin frost or a surface glaze. A deposit of frozen nitrogen, estimated to be at least 2.5 miles deep in some regions, so massive and so dense that its weight may have literally tipped Pluto on its axis through a process called true polar wander, reorienting the entire world, so the basin now sits almost precisely opposite Pluto's largest moon, Charon. The nitrogen ice in Sputnik Planitia is not static, it is moving, slowly, continuously, driven by heat leaking upward from Pluto's deep interior. The surface of the basin is carved into vast polygonal cells, each one roughly 20 to 25 miles across, where warmer nitrogen ice rises in the center, spreads outward across the surface as it cools, and then sinks back down along the cell margins. These are convection patterns. The same process that drives thunderstorms in Earth's atmosphere and ocean currents in the Atlantic is happening inside a sheet of frozen nitrogen on a world nearly 4 billion miles from the sun. The ice is churning. overturning. Moving with a ponderous patience that takes roughly 500,000 years per full cycle of upwelling and sinking. There is nothing like it anywhere else in the explored solar system. It is unique to Pluto. Along the western and southern edges of Sputnik Planitia, mountains rise. Not gentle hills, mountains of frozen water ice standing up to 2.5 miles high, with some reaching nearly 3.5 miles above the surrounding terrain. Water ice at Pluto's temperatures is structural material. It does not melt, it does not bend. It supports topography the way granite supports mountains on Earth. These ranges, named after explorers and mountaineers, are thrust up along the margins of the basin by tectonic forces that scientists are still working to fully characterize. Some of the mountains appear to be enormous blocks of water ice that carved away from the basin rim and were carried inward by the flowing nitrogen, where they now drift like icebergs on a frozen sea, slowly migrating toward the edges of convection cells and clustering in the troughs between them. Blocks of ice, the size of city districts, floating and drifting across a churning plain of frozen nitrogen. On a world that was supposed to be dead. East of the heart, glaciers of solid nitrogen flow down from pitted highlands into the basin. These are actual glaciers, not a metaphor, not an approximation. Flowing rivers of frozen nitrogen that carve valleys, leave behind dark debris trails resembling terrestrial moraines, and merge into the main body of Sputnik Planitia in patterns that are startlingly similar to the glacial systems of Greenland and the Antarctic Peninsula. Except these glaciers are not water, they are nitrogen. And they move across a landscape colder than anything most humans have ever been asked to imagine. Further east, the terrain transforms into something that exists nowhere else in the imaged solar system. Fields of enormous blades made of methane ice stretch across the equatorial highlands in a region called Tartarus Dorsa. Each blade rises hundreds of feet into the thin air. Some estimates suggest the tallest formations reach over 1,000 feet. They are arranged in parallel ridges, separated by deep troughs, extending across thousands of square miles. Scientists call this bladed terrain. The structures are thought to have grown over tens of millions of years through the deposition of methane ice from the atmosphere, followed by erosion through sublimation, the process by which a solid converts directly to vapor without passing through a liquid phase. These methane skyscrapers may be the most widespread landform on Pluto's far side, the hemisphere that was in shadow during the New Horizons flyby and could only be imaged at low resolution. They have no known analog on any other world that has ever been explored. They are unique in the solar system. West of the heart, a dark equatorial band called Cthulhu Macula stretches for thousands of miles, stained nearly black by tholins, organic compounds settling from the atmosphere. It is ancient, heavily cratered, and among the darkest terrain on Pluto. And south of Sputnik Planitia, the landscape changes again. Here, enormous dome-shaped structures rise from the terrain. Right Mons, the largest confirmed feature of this kind, stretches roughly 90 miles across its base and rises approximately 3 miles above the surrounding plains. It has a deep central depression at its peak. In scale, it is comparable to Mauna Loa, the largest shield volcano on Earth. But Right Mons was not built by eruptions of molten rock. It was built by cryovolcanism, ice volcanism. A thick slurry of partially frozen water mixed with ammonia and other volatile compounds, oozed upward from reservoirs beneath the ice shell, spread across the surface under its own weight, and froze into permanent landforms. Researchers describe the material as having the consistency of toothpaste or ketchup, not a free-flowing liquid, not a rigid solid, something in between. extruding from volcanic vents and piling up into broad, low shields, miles wide and miles high. The terrain around Right Mons has almost no impact craters. On a body that is 4.5 billion years old, a surface with virtually no craters is a surface that has been recently resurfaced. Something erased the record of ancient impacts. Something renewed the ground. The best estimates place this cryovolcanic activity within the last 100 to 200 million years. In geological terms, that is recent. And a separate analysis of a feature called Kiladze, a roughly 27-mile-wide depression northeast of Sputnik Planitia, suggests it may be a volcanic caldera rather than an impact crater, with chemical evidence of cryovolcanic effusion potentially within the last few million years, not billion, million. On a world nearly 4 billion miles from the Sun, something erupted onto the surface within a time frame so recent that early humans may have already been walking the savannas of Africa when it happened. None of this was predicted. None of this fits the model of a small, dead, frozen world at the end of the solar system. The convection in Sputnik Planitia requires interior heat. The cryovolcanism requires a source of liquid or semi-fluid material beneath the ice shell. The absence of craters on young terrains demands active resurfacing mechanisms. The question that every one of these findings pointed toward was always the same. Where is the heat coming from? The leading answer is radioactive decay. Pluto's rocky core, which makes up roughly 2/3 of the world's total mass, contains long-lived isotopes of uranium, thorium, and potassium that disintegrate over billions of years, releasing persistent amounts of thermal energy. On Earth, this same process contributes significantly to keeping the planet's interior molten. On Pluto, the total heat production is far smaller. But Pluto is also far smaller. And, critically, newer thermal models suggest that the composition of Pluto's ice shell includes materials with insulating properties far more powerful than ordinary water ice. Those materials, and the mechanism by which they work, change the entire picture of what Pluto's interior could sustain. The full explanation of that mechanism is coming, but the conclusion it points toward can be stated now. With the right insulation in place, models can sustain a subsurface ocean of liquid water beneath the ice shell for the entire age of the solar system. A subsurface ocean. On Pluto, a body of liquid water, possibly laced with ammonia and dissolved salts that lower the freezing point, existing in permanent darkness beneath miles of frozen ice, kept from solidifying by the quiet patience of radioactive atoms breaking apart in the core above. Multiple independent lines of evidence now converge on this conclusion. The orientation of Sputnik Planitia relative to Charon requires a subsurface mass anomaly consistent with an ocean. The extensional fractures across Pluto's surface match models of a thickening ice shell expanding as a deeper ocean slowly freezes. The cryovolcanism requires a source of mobile fluid. And the thermal physics, once the insulating clathrate is included, can keep water liquid beneath the ice for 4.5 billion years. Pluto is now classified among the ocean worlds of the solar system, a category previously reserved for the moons of giant planets where powerful tidal forces keep interiors warm. A world nearly 4 billion miles from the Sun, where noon looks like twilight and the temperature sits 40 degrees above the point where atoms stop moving, may harbor liquid water beneath its surface in a place where no one believed it could persist. That is not the Pluto anyone was taught about in school. That is not the Pluto from the poster on the classroom wall. That is not the frozen marble from the mnemonic device. And the surface, extraordinary as it is, represents only half of the revelation. Because above the ice and the mountains and the glaciers and the volcanoes, Pluto has something else that nobody fully anticipated, something that changes the meaning of this world in ways that are even more unsettling. An atmosphere, a thin, layered, photochemically active atmosphere that behaves unlike any other atmosphere in the solar system. An atmosphere whose energy balance is controlled by haze particles, in a way confirmed by the James Webb Space Telescope in 2025 and observed at no other known world. An atmosphere that is actively losing molecules to space, molecules that drift through the vacuum and settle onto the poles of Pluto's own moon, Charon, staining them dark red. That atmosphere, what it does, what it means for anyone who tries to imagine standing on this world, and what it reveals about the true hostility of Pluto as a place, is where this story turns next. Because what makes Pluto terrifying is not any single feature, it is the accumulation. It is the slow, relentless realization that this world, dismissed for nearly a century as a frozen afterthought, is one of the most geologically active, environmentally extreme, and psychologically alien places the human species has ever managed to photograph. And we have only seen half of its surface. The other half was in shadow when New Horizons flew past. We do not know what is there. So far, we have laid out what New Horizons saw. Convection cells churning across Sputnik Planitia, mountains of water ice, nitrogen glaciers carving valleys, cryovolcanic domes the size of shield volcanoes on Earth, bladed terrain made of methane ice with no analog anywhere else in the explored solar system, a surface with ages ranging from billions of years to possibly less than 10 million. The inventory was extraordinary. But an inventory is not an explanation, and the explanation is where the real strangeness begins. Because the question that every one of those features forces you to confront is not what is there, it is how any of it is possible. The instruments that produced this picture were not designed with complexity in mind. New Horizons carried 7 science instruments, built under a mass budget so tight that the entire spacecraft weighed roughly 1,054 pounds, about the mass of a concert grand piano. The payload had to be small, light, power-efficient, and capable of operating autonomously for hours during the closest approach while the spacecraft was out of contact with Earth. Every instrument was chosen to answer questions that scientists in the early 2000s thought were the right questions to ask about a small frozen body at the edge of the solar system. The fact that those instruments captured evidence of a world far more complex than anyone anticipated is partly a tribute to clever engineering and partly a measure of how wrong the expectations were. The camera system that produced the iconic surface images is called LORRI, the Long-Range Reconnaissance Imager. It is a telescopic camera with a 20-centimeter aperture that captured black and white images at resolutions down to roughly 80 meters per pixel at closest approach. That is sharp enough to see features the size of a football field from nearly 8,000 miles away. LORRI was designed for long-range targeting and navigation as much as for science, but during the flyby, it produced the highest resolution images of Pluto's surface that exist. Every mountain, every convection polygon, every blocky ice fragment floating on Sputnik Planitia that we have already described was photographed by this single telescope in a window of hours before the geometry of the encounter carried the spacecraft past and away. The color and composition data came from a different instrument called RALPH, which combined a visible light color imager with an infrared spectrometer called LISA, the Linear Etalon Imaging Spectral Array. LISA measured the spectrum of sunlight reflected from Pluto's surface at wavelengths between 1 and 2.5 microns, deep into the near-infrared, where different ice species have distinct spectral fingerprints. It was LISA that mapped the distribution of nitrogen ice, methane ice, carbon monoxide ice, and water ice across Pluto's surface. It was LISA that detected the spectral signature of ammonia-bearing compounds around suspected cryovolcanic features. And it was LISA that revealed the compositional contrast between the ancient, dark, tholin-covered terrain of Cthulhu Macula and the fresh, bright nitrogen ice plains of Sputnik Planitia in quantitative chemical terms rather than just visual ones. Without LISA, the mountains would have been shapes without identity. The glaciers would have been flows without chemistry. The volcanoes would have been domes without composition. The spectrometer turned images into science. A third instrument, REX, the radio science experiment, used the spacecraft's communication antenna to perform a radio occultation as New Horizons passed behind Pluto, as seen from Earth. The spacecraft transmitted a signal toward Earth, and as that signal passed through Pluto's atmosphere, it was bent and absorbed in measurable ways that allowed scientists to determine the atmospheric pressure at the surface, the temperature profile with altitude, and the structure of the lower atmosphere. REX confirmed the surface pressure at roughly 11 microbars and measured the near-surface atmospheric temperature at approximately -388 degrees Fahrenheit, consistent with the extreme surface cold measured by other means. The instrument also provided constraints on the radius and density of Pluto that refined interior models significantly. A fourth instrument, ALICE, an ultraviolet spectrometer, studied Pluto's upper atmosphere by observing how sunlight and the light of a background star were absorbed as they passed through the atmosphere at different altitudes. ALICE detected the nitrogen, methane, and other hydrocarbon species in the upper atmosphere and measured the rate at which atmospheric gases were escaping into space. The data from ALICE was critical in establishing that Pluto's atmosphere was losing material to the surrounding environment at rates that, while lower than initial estimates, were still significant enough to require a replenishment mechanism. Something had to be supplying nitrogen and methane to the atmosphere on geological timescales, or it would have been lost to space entirely. Cryovolcanism and surface sublimation from Sputnik Planitia are the leading candidates for that replenishment. Two particle instruments, SWAP and PEPSSI, measured the interaction between Pluto's escaping atmosphere and the solar wind, the stream of charged particles flowing outward from the Sun. They found that Pluto's atmospheric escape creates a region of disturbed plasma extending tens of thousands of miles downstream, a cometry-style interaction where the escaping nitrogen molecules are ionized by ultraviolet light and swept up by the solar wind. In a very real sense, Pluto has a tail. Not a visible tail, not a comet's dusty streamer, but a measurable trail of ionized atmospheric gas flowing away from the world and into the outer solar system. The dwarf planet is slowly losing itself to space. Together, these instruments painted a picture that was scientifically rigorous, compositionally detailed, and geologically devastating to the old models. And the deepest devastation was not at the surface. It was in the interior. Because every active process visible on Pluto's surface, from the convective churning of Sputnik Planitia to the eruption of cryolava onto the Reitmans region, requires heat. And heat, in a body this small and this old, requires an explanation that the standard thermal models of 2015 could not easily provide. The problem is fundamental. Pluto's rocky core, which constitutes roughly 65 to 70% of the world's diameter, generates heat through the radioactive decay of long-lived isotopes, primarily uranium-238, thorium-232, and potassium-40. This is the same process that contributes to Earth's internal heat budget. But the total amount of radioactive material in Pluto's core is proportional to the core's mass, which is small. Estimates of Pluto's total radiogenic heat production yield a figure on the order of a few milliwatts per square meter at the surface. For comparison, Earth's internal heat flux is roughly 90 milliwatts per square meter. Pluto's heat budget is a fraction of Earth's. The question is whether that fraction is enough. Before New Horizons, most thermal evolution models said no. A standard model would begin with Pluto forming hot, differentiated early, and then cooling monotonically over 4.5 billion years. The ice shell would thicken steadily as the subsurface cooled. The interior would freeze from the outside in. Any liquid water that existed early in Pluto's history would solidify within the first 1 to 2 billion years, and the world would become geologically inert. End of story. No convection, no volcanism, no tectonics, no ocean. Just a frozen core wrapped in a frozen shell, orbiting a distant star in permanent silence. The critical variable that changed this picture is thermal conductivity. Specifically, the thermal conductivity of the material that separates Pluto's warm, rocky core from its cold outer surface. In the simple models, that material was treated as ordinary water ice, which is a reasonably good thermal conductor as insulators go. Water ice transmits heat efficiently enough that even modest radiogenic heating in the core would be conducted outward to the surface and radiated away into space relatively quickly. Under those assumptions, the interior cools fast and the ocean freezes early. But Pluto's ice shell is not made of ordinary water ice alone. It contains methane. And when methane is present in the right proportions at the right pressures, it does not simply mix into the water ice. It forms a distinct crystalline structure called a clathrate hydrate. A clathrate is a cage compound, a lattice of water molecules arranged in a regular geometric framework with methane molecules trapped inside the cages like prisoners in individual cells. The structure is rigid, stable at the pressures and temperatures found inside Pluto's ice shell, and critically, it is a far worse thermal conductor than pure water ice. The thermal conductivity of methane clathrate hydrate is roughly 5 to 10 times lower than that of crystalline water ice. It is also more viscous, meaning it resists convective flow more strongly. If a layer of methane clathrate exists within Pluto's ice shell, and the thermodynamic conditions inside Pluto are consistent with its formation, it acts as an insulating blanket. The modest heat trickling upward from the radioactive core gets trapped beneath the clathrate layer. It cannot conduct outward efficiently. The temperature beneath the clathrate rises. The ice above the clathrate stays cold and rigid, while the ice below it stays warm and potentially liquid. The ocean does not freeze. It persists, protected by a thermal barrier that the pre-New Horizons models did not include because no one had reason to think it mattered. This mechanism was proposed in detail by Shunichi Kamata and colleagues in a study that examined whether a clathrate insulating layer could explain both the preservation of a subsurface ocean and the specific gravitational characteristics of the Sputnik-Planitia Basin. As described earlier, the basin sits almost directly opposite Charon on the tidal axis, a position reached through true polar wander. For that reorientation to have occurred, the crust and mantle must have been decoupled, which requires a liquid or near-liquid layer between them. Kamata's model showed that a clathrate layer of appropriate thickness could maintain a subsurface ocean for the entire age of the solar system, while also keeping the outer ice shell cold and rigid enough to support the observed topographic variations across Pluto's surface. The models simultaneously explained the ocean's survival and the crust's structural integrity. It was elegant, physically grounded, and consistent with the New Horizons data. The implications extend far beyond Pluto's own geology. If a clathrate insulating layer is all it takes to preserve a liquid water ocean inside a small icy body for 4.5 billion years, then the conditions for ocean persistence are far less demanding than previously assumed. The traditional ocean worlds, Europa, Enceladus, Titan, and Ganymede, are moons of giant planets. Their oceans are maintained primarily by tidal heating, the enormous gravitational energy generated by their orbital interactions with Jupiter or Saturn. Pluto has no giant planet. It has no significant tidal energy source. Its ocean, if it exists, is maintained by nothing more than the quiet decay of radioactive atoms in its rocky core and the insulating properties of a clathrate shell. That changes the equation for the entire outer solar system. The Kuiper Belt contains an estimated number of Pluto-sized and somewhat smaller bodies in the hundreds to thousands. Many of them differentiated early. Many of them have rocky cores with radioactive inventories comparable to Pluto's. Many of them formed with methane in their interiors, providing the raw ingredient for clathrate formation. If the clathrate mechanism works for Pluto, it should work for a substantial fraction of these bodies as well. The logical conclusion, which several research teams have now drawn independently, is that subsurface oceans may be common among dwarf planets and large Kuiper Belt objects. Not guaranteed, not universal, but common. The outer solar system might contain dozens of ocean worlds that no one has visited, no one has imaged, and no one has seriously considered as candidates for liquid water until Pluto forced the question open. This has implications for astrobiology that are difficult to overstate. The search for environments that could support life has historically focused on two criteria: liquid water and an energy source. The inner solar system provides abundant solar energy but limited liquid water outside of Earth. The moons of the giant planets provide liquid water through tidal heating, but exist in harsh radiation environments and complex gravitational systems. The Kuiper Belt has always been dismissed as too cold, too dark, and too remote to matter. But if Pluto and its neighbors harbor subsurface oceans maintained by radiogenic heat and clathrate insulation, then the volume of habitable real estate in the solar system is vastly larger than anyone imagined even a decade ago. It extends from the orbit of Neptune to the edge of the Sun's gravitational influence, in a region of space thousands of times larger than the inner solar system, populated by thousands of icy worlds with interiors that may be warm, wet, and chemically active. Nobody is claiming that life exists in Pluto's subsurface ocean. The evidence is nowhere near sufficient for such a claim. But the discovery that the ocean likely exists at all, on a body where it was considered nearly impossible, has expanded the conceptual boundaries of where scientists are willing to look. The New Horizons mission did not just reveal Pluto's surface, it revealed a principle. Small, cold, distant worlds can retain liquid water if their interiors are insulated properly. And that principle applies not just to one world at the edge of the solar system, but, potentially, to an entire population of worlds that we have barely begun to catalogue. The thermal story beneath Pluto's surface connects directly to the features visible above it. The convection in Sputnik Planitia is driven by the heat that the clathrate layer traps. The cryovolcanism at Right Mons and possibly Kiladze requires a reservoir of mobile material, likely water mixed with ammonia and dissolved volatiles, that can only exist if the interior is warm enough to maintain liquid at depth. The extensional faults that crisscross Pluto's surface are the scars of that gradual solidification, the crust cracking outward as the frozen shell thickens at the ocean's expense. Every geological feature is a surface expression of the thermal story playing out in the interior. And the thermal story once the clathrate mechanism is understood, makes physical sense in a way that the pre-New Horizons models did not. Pluto is not defying physics. It is obeying a more complete version of physics than anyone had bothered to apply to it before. The interior is warm. The shell is insulated. The ocean endures. And the surface records every chapter of that hidden thermal story in landscapes that were never supposed to exist. And there is one more feature of Pluto's surface that ties the geological story together in a way that is both scientifically precise and deeply strange. The dunes. Along the northwestern margin of Sputnik Planitia, where the nitrogen ice plain meets the water ice mountains of Al-Idrisi Montes, New Horizons imaged a field of regularly spaced parallel ridges that extend across at least 45 miles of terrain. They are spaced roughly half a mile to a mile apart. They are oriented perpendicular to the expected wind direction, and they are, by every analysis that has been applied to them, dunes. Wind-blown accumulations of granular material deposited in the same aerodynamic patterns that produce sand dunes in Earth's deserts. The grains are not sand. They are particles of methane ice, roughly the size of coarse sand grains, likely eroded from the nearby mountains and carried by winds blowing across the basin. The winds themselves are driven by the daily sublimation cycle of nitrogen ice in Sputnik Planitia. As the faint sunlight warms the surface during the day, nitrogen ice sublimates into gas, generating near-surface winds that blow outward from the basin. At night, the process reverses. This daily breathing of the nitrogen heart creates a wind system capable of lifting and transporting methane ice grains across the landscape and depositing them in organized dune fields. Dunes require three things: particles small enough to be moved by wind, winds strong enough to move them, and a supply mechanism to keep providing new particles. Pluto has all three. On a world where the air is so sparse, it would register as emptiness by any instrument designed to measure weather on Earth, with gravity 1/16 that of our planet, with surface temperatures that would freeze every gas in the room you are sitting in. There are dunes. The same fundamental process that builds the great ergs of the Sahara and the rippled surfaces of Martian basins is operating on the surface of Pluto, 3.7 billion miles from the Sun, in an atmosphere thinner than the best vacuum most laboratories can produce. The physics does not care about distance. It does not care about temperature. It does not care about how far you are from the nearest human being. If the conditions are met, the process runs. And on Pluto, the conditions are met in ways no one predicted. When you step back from the individual features and look at the full geological picture of Pluto as revealed by New Horizons and refined by subsequent analysis, what you see is not a dead world. It is not a dying world. It is a world that is, by every meaningful geological standard, alive. Its surface is being reworked by convection, glaciation, sublimation, wind transport, volcanic extrusion, tectonic faulting, and atmospheric deposition. Its interior retains enough heat to drive processes that reach the surface and reshape it on timescales that are short by geological reckoning. Its chemistry is complex enough to involve multiple distinct ice species, organic tholins, ammoniated compounds, and possibly liquid water at depth. And its landscape includes features that exist nowhere else in the explored solar system, products of a unique combination of temperature, composition, gravity, and distance that has no parallel. The expectation was death. The reality was activity. The expectation was simplicity. The reality was a world whose geological diversity rivals planets many times its size. The expectation was that the edge of the solar system would be boring. The reality was the opposite. And the geology is only one part of the story, because above Pluto's restless surface there is an atmosphere that turned out to be just as strange, just as unexpected, and just as difficult to explain. An atmosphere that the James Webb Space Telescope recently confirmed operates by a mechanism found nowhere else in the solar system. An atmosphere that is, in a very literal sense, slowly leaking off the world and settling on the frozen face of its companion. Pluto does not keep its secrets to itself. It shares them with Charon, molecule by molecule, drifting silently through the vacuum between two worlds locked together at the edge of sunlight. Most people do not know that Pluto has an atmosphere. It is not an obvious fact. Nothing about the popular image of Pluto suggests it. A world that small, that cold, that distant from any significant energy source should not be able to hold onto a layer of gas. The gravity is too weak, the temperatures are too low. The solar wind, even as faint as it is at that distance, should have stripped any atmosphere away long ago. And yet Pluto has one. It is thin. It is fragile. It is made of gases that would freeze solid on any surface you have ever touched. And it behaves in ways that have no analogue anywhere else in the solar system. The atmosphere was not discovered by New Horizons. Astronomers had known about it since 1988, when Pluto passed in front of a distant star as seen from Earth, an event called a stellar occultation. As the star's light passed through the region around Pluto just before disappearing behind the disk, it dimmed gradually rather than winking out sharply. That gradual dimming was the signature of an atmosphere, a thin shell of gas refracting and absorbing the starlight as it passed through. Subsequent occultations refined the measurements. By the 2010s, astronomers had established that Pluto's atmosphere was composed primarily of nitrogen, with traces of methane and carbon monoxide. The surface pressure was roughly 11 microbars, which is approximately 100,000 times less than the atmospheric pressure at sea level on Earth. To put that in human terms, Pluto's atmosphere is thinner than the best laboratory vacuum most university physics departments can achieve. It is a ghost of an atmosphere, a whisper of gas clinging to the surface by the barest margin of gravitational retention. But it is there. And when New Horizons arrived in 2015 and looked back at Pluto after passing it, with the sun behind the dwarf planet, the atmosphere lit up. The backlit images showed something extraordinary. Layer after layer of haze, stacked in thin horizontal bands extending more than 100 miles above the surface. The hazes were blue. Not a deep, vivid blue like Earth's sky, but a pale, cold, ethereal blue that comes from the scattering of sunlight by very small particles. The particles are not water droplets. They are not ice crystals in any familiar sense. They are tholins, the same complex organic molecules that coat the dark equatorial regions of Pluto's surface, formed by photochemical reactions in the upper atmosphere, where ultraviolet light from the distant sun breaks apart methane and nitrogen molecules, and the fragments recombine into larger, more complex hydrocarbons and nitriles. These tholin particles are tiny, much smaller than the wavelength of visible light, and they scatter short wavelength blue light preferentially, producing the blue haze layers that New Horizons photographed in what became one of the mission's most iconic images. The haze layers are not uniform. They appear at distinct altitudes, separated by gaps, in a pattern that suggests they are formed by atmospheric waves, oscillations caused by wind flowing over topographic features on the surface below, similar in principle to the Lee waves that form clouds over mountain ranges on Earth. The comparison is inexact because the atmospheric physics is radically different, but the underlying mechanism, topography, forcing vertical motions in a flowing atmosphere, appears to apply. The result is a sky that, if you could see it from the surface, would be unlike anything a human has ever witnessed. The atmosphere is too thin to scatter enough light to produce a bright sky. Standing on Pluto's surface during the day, the sky above you would be essentially black, the way it looks from the surface of the moon. But near the horizon, especially during the long twilight that accompanies sunrise and sunset, on a world with a 6.4 Earth-day rotation period, the haze layers would become visible as faint, luminous bands, pale blue streaks of light arcing across the lower sky. The mountains would cast shadows into the haze, long dark fingers stretching across the twilight landscape. New Horizons actually captured images of this happening. The backlit photographs show the silhouettes of Pluto's mountains, with haze layers glowing softly beyond them, illuminated by sunlight filtering through the atmosphere at a shallow angle. It is one of the most hauntingly beautiful images in the history of planetary exploration. And it comes from a world where the temperature is 230 degrees below zero and the sun is a bright star. For years after the flyby, the precise role of these haze particles in Pluto's atmospheric physics remained an open question. New Horizons had measured the temperature of Pluto's upper atmosphere and found something puzzling. The temperature at altitude was far colder than models predicted. Standard atmospheric physics, applied to a nitrogen-dominated atmosphere heated by absorption of sunlight and cooled by molecular emission, predicted an upper atmosphere temperature of approximately -280 degrees Fahrenheit. The actual measured temperature was far colder, closer to -330 degrees Fahrenheit. A gap of 50 degrees may not sound dramatic in everyday terms, but at temperatures this close to absolute zero, it represents a massive discrepancy in the energy balance, one that no known gas phase process could account for. Something else was pulling heat out of the upper atmosphere with an efficiency that the standard models had no mechanism to produce. In 2017, Shi Jiang, a planetary scientist at the University of California, Santa Cruz, proposed a hypothesis that many of his colleagues initially considered improbable. He argued that the haze particles themselves were controlling the atmospheric energy balance. The tholins, he suggested, were absorbing solar energy at certain wavelengths and re-emitting it as thermal radiation in the mid-infrared, essentially acting as the atmosphere's primary cooling mechanism. In gas-dominated atmospheres like Earth's, molecules handle most of the radiative energy transfer. In Pluto's atmosphere, Jiang proposed, the haze particles had taken over that role entirely. The atmosphere was being cooled by its own organic smog. Jiang made a clear, testable prediction. If the haze particles were responsible for cooling the atmosphere, they should be emitting detectable mid-infrared radiation. The signal would be faint, far too faint for any ground-based telescope or any instrument in operation at the time, but it should be there. He published the prediction and waited. The instrument capable of testing it arrived on Christmas Day, 2021, when NASA launched the James Webb Space Telescope. In 2022 and 2023, JWST turned its mid-infrared instrument toward Pluto. The observations, led by Tanguy Bertrand of the Observatoire de Paris, produced results published in a series of papers in 2025, including a study in Nature Astronomy that confirmed Jiang's hypothesis. JWST detected the thermal emission of Pluto's haze in the mid-infrared, measured its spectral characteristics, and demonstrated that the haze largely controls the atmospheric energy balance. The haze particles are composed of a mixture of titangent-like organic materials and ices of hydrocarbons and nitriles, and they radiate heat efficiently enough to keep Pluto's upper atmosphere far colder than it would otherwise be. The confirmation was precise, quantitative, and unambiguous. Pluto's atmosphere operates by a mechanism that exists nowhere else in the solar system. On every other world with a substantial atmosphere, gas molecules dominate the energy balance. On Pluto, solid organic particles do. The atmosphere is being regulated by its own slowly falling haze, a system of climate control built from photochemical smog at the edge of the solar system. That finding has implications beyond Pluto. Researchers have noted that similar nitrogen-methane hydrocarbon haze chemistry likely existed in Earth's own atmosphere before the Great Oxidation Event, the period roughly 2.4 billion years ago, when photosynthetic organisms began flooding the atmosphere with oxygen. Before that transition, Earth's atmosphere was rich in methane and nitrogen and would have produced organic hazes through similar photochemical pathways. Understanding how Pluto's haze controls its atmosphere could provide insights into the conditions that prevailed on early Earth during the period when life was first emerging. Pluto, in this sense, is not just an alien world. It is a laboratory for studying atmospheric chemistry that once operated on our own planet, preserved in the deep freeze of the outer solar system like a sample sealed in ice. But the JWST observations revealed something else about Pluto's atmosphere that is even stranger and more unsettling than the haze cooling. Mechanism. Something is leaving Pluto. Methane molecules, energized by the absorption of extreme ultraviolet light from the sun in the upper atmosphere, gain enough thermal energy to exceed Pluto's escape velocity. They leave. They drift upward and outward, crossing the thin boundary where Pluto's gravity can no longer hold them, and they enter the space between Pluto and its largest moon, Charon. Some of those molecules travel the roughly 12,000 miles separating the two bodies, reach Charon, and settle onto its surface. This is not a metaphor. This is a measured, observed physical process. Molecules from Pluto's atmosphere are being deposited onto the poles of Charon, where they accumulate and are subsequently altered by radiation and photochemistry into the dark reddish material that gives Charon's north pole its distinctive color, a feature informally named Mordor macula. The JWST data confirmed and refined this picture by measuring the thermal properties and rotational light curves of both Pluto and Charon separately for the first time in the mid-infrared. The measurements allowed researchers to constrain the surface properties of Charon's different terrains and to trace the connection between Pluto's atmospheric composition and the material accumulating on Charon's poles. The process is unique in the solar system. No other pair of bodies in any known planetary system exhibits this kind of atmospheric transfer, where one world's atmosphere slowly drains onto the face of its companion. It is an intimacy between two worlds that is difficult to describe without anthropomorphizing, and yet it is entirely mechanical, entirely governed by physics, entirely indifferent to the strangeness of what it produces. Pluto is bleeding into Charon. Molecule by molecule, year by year, one world's sky becomes the other world's ground. Pluto's atmosphere is also temporary, in a way that no other planetary atmosphere is. Pluto's orbit around the Sun is highly eccentric. Its distance from the Sun ranges from roughly 2.7 billion miles at its closest to 4.6 billion miles at its farthest. That variation is not subtle. At its closest approach to the Sun, which last occurred in 1989, Pluto receives significantly more solar energy than at its farthest point. The increased warmth, feeble as it is enough to sublimate nitrogen ice from the surface and thicken the atmosphere. As Pluto recedes from the Sun over the following decades and centuries, the atmosphere cools, nitrogen condenses back onto the surface, and the atmosphere thins. Over the full 248 Earth-year orbital period, Pluto's atmosphere may undergo dramatic cycles of inflation and collapse. Some models suggest that at its farthest point from the Sun, Pluto's atmosphere could collapse entirely, freezing out onto the surface in a thin layer of frost, leaving the world temporarily airless. Other models suggest that enough thermal inertia and haze-driven radiative effects keep at least a vestige of atmosphere present throughout the orbit. The question is still debated. What is not debated is that the atmosphere is transient. It is a seasonal phenomenon on a 248-year time scale. The atmosphere you would encounter if you visited Pluto today is not the atmosphere that will exist 2 centuries from now. The world breathes on a cycle longer than any human civilization has lasted. And that brings us to the question that the geological and atmospheric story has been building toward. The question that transforms Pluto from a scientific curiosity into something that touches a different nerve entirely. What would it actually be like to be there? Not as a data point, not as a temperature reading or a pressure measurement or a spectral signature. What would it mean to stand on the surface of Pluto with human eyes, human skin, human lungs? A human nervous system evolved over millions of years in a world of warmth, light, oxygen, and gravitational comfort. What would that experience be? Begin with what you would see. You are standing on a plain of nitrogen ice. The surface beneath your feet is pale, slightly translucent, and smooth in a way that suggests slow geological processing rather than weathering. It is dimly lit. The sun hangs in the sky, somewhere above the horizon, but it is not the sun, you know. It is a point of light, intensely bright compared to the stars around it, but small, smaller than you have ever seen it. Not a disk, not a circle with visible edges, a fierce, concentrated dot that would fit inside the period at the end of a printed sentence. The light it provides is real, but thin. The landscape around you is visible, but only in the way a moonlit landscape on Earth is visible. You can see shapes, contours, and colors, but everything is muted. There are no strong shadows, no vivid contrasts. The dominant color of the surface is pale yellowish white, where nitrogen ice dominates, shading to darker amber and red, where tholins have accumulated. Near the horizon, if you are positioned where you can see the haze layers, there is a faint blue glow, barely perceptible, that traces the curve of the world. The sky above is black. Not the dark blue of a clear night on Earth, where scattered sunlight and airglow give the sky a residual brightness. Black. The stars are visible in full daylight, sharp and unblinking, in an atmosphere too thin to produce the twinkling effect that Earth's atmosphere creates. The Milky Way stretches overhead with a clarity that no one on Earth's surface has ever seen, not because the view is better here, but because there is no atmosphere to get in the way. The sky is space. You are looking directly into the void from a surface that barely qualifies as having an atmosphere at all. The silence is total. On Earth, even in the quietest environments, there is always sound. Wind moving across surfaces, the hum of distant atmospheric activity, the faint vibration of a living planet transmitted through the ground. On Pluto, the atmosphere is too thin to carry sound in any way that a human ear could perceive. If you shouted, the sound waves leaving your mouth would propagate through the near vacuum so weakly that someone standing 10 feet away without a radio link would hear nothing. The world is mute, not quiet. Mute. The concept of sound as a natural feature of the environment does not apply here. The temperature is approximately -387 degrees Fahrenheit. At this temperature, any exposed human skin would not merely freeze. The tissue would undergo a process closer to vitrification, the transformation of biological material into a glass-like solid as all molecular motion ceases. It would not hurt, because the nerve endings responsible for pain would stop functioning almost instantly. The cold on Pluto is not an extreme version of cold as humans experience it. It is a different category. It is the absence of thermal energy on a scale that the human body has no mechanism to register because evolution never needed to equip us for it. No organism on Earth has ever been exposed to temperatures this low in a natural environment. The deepest Antarctic winter, the coldest laboratory cryogenic bath, the most extreme conditions ever endured by a living cell on this planet, are all hundreds of degrees warmer than Pluto's surface. The gravity is roughly 6% of Earth's. You weigh about 1/16 of what you weigh on Earth. A person who weighs 180 pounds at home would weigh roughly 11 pounds on Pluto. You could jump to extraordinary heights with minimal effort. A casual hop would carry you several feet off the surface. A running leap could send you soaring to the height of a 2-story building. The motion would feel dreamlike, slow, floaty, disconnected from the muscular feedback your body expects. Every movement would feel wrong. Not painful, not dangerous, just wrong. The fundamental calibration between effort and result that your nervous system uses to navigate the physical world would be off by a factor of 16. You would stumble, you would overshoot. You would feel, at every moment, that you are not where your body thinks you are. The atmosphere around you is composed of nitrogen, methane, and carbon monoxide. None of these are breathable. Nitrogen is inert and would not support respiration. Methane is flammable, but not in the absence of oxygen, which does not exist in any detectable amount on Pluto. Carbon monoxide is actively toxic to human biology, binding to hemoglobin with an affinity roughly 240 times greater than oxygen, and effectively suffocating the blood's ability to carry oxygen to tissues. But the toxicity is irrelevant because the atmospheric pressure is so low that your lungs could not function regardless of composition. At 11 microbars, the gas molecules are so sparse that the mechanical process of breathing, which relies on a pressure differential between the atmosphere and the lungs, cannot operate. You would not suffocate from breathing poison. You would suffocate from breathing nothing. The air is there. Your lungs cannot use it. The distinction is academic. The result is the same. Now add the distance. You are 3.7 billion miles from Earth. A radio signal, traveling at the speed of light, takes approximately 5.5 hours to reach you from mission control. If you sent a distress call the moment you arrived, the earliest you could receive a response would be roughly 11 hours later. In practice, the delay would be longer. The deep space network antennas that communicate with spacecraft in the outer solar system are shared resources, scheduled in advance and allocated by priority. You are not just far away. You are far away in a way that makes real-time communication impossible and rescue a logistical absurdity. There is no scenario, with any technology that currently exists or is likely to exist within the next century, in which a human being in distress on Pluto's surface could be reached by another human being in less than years. The isolation is not like being in a remote wilderness or adrift at sea. Those situations, however desperate, still involve distances measured in hundreds or thousands of miles and rescue times measured in hours or days. On Pluto, the distance is measured in billions of miles, and the rescue time is measured in decades, if it is measured at all. And here is where the psychological dimension becomes difficult to articulate with precision, but impossible to ignore. The isolation of Pluto is not merely physical, it is existential. You are standing at the outermost edge of the sun's meaningful influence, on a world that exists in a twilight so deep that daylight is indistinguishable from what most humans would call night. The warmth of the sun, the energy source that powers every biological process on Earth, that drives the winds, that evaporates the oceans, that grows the food you eat, is present here only as a faint optical point that provides no perceptible heat. You can see it, you can measure it, but you cannot feel it. The sun, from Pluto's surface, is functionally a star. The brightest star in the sky, but a star nonetheless. The psychological architecture of being on a planet, the unconscious certainty that there is a warm, powerful, nurturing light source overhead that defines day and night and seasons and life, does not apply. You are not on a planet in the way your brain understands that concept. You are on a frozen object orbiting a star that happens to be slightly closer than the others. This is what separates Pluto's hostility from the hostility of every other dangerous world humans have studied. On other worlds, the threat comes from forces turned up past the point of survival, a furnace atmosphere, a crushing sky, a bath of charged particles, a gravitational field that pins you to the ground. The human brain can categorize those hazards. It has names for them. It can imagine them as extreme versions of conditions it already knows. The danger is quantitative. It is a dial turned beyond the safe range on a scale that still makes sense. Pluto's hostility is different in kind, not in degree. It does not fit on any familiar scale. Pluto's hostility is the hostility of alienness itself. It is a world where the ground is made of frozen air, where the mountains are ice harder than rock, where glaciers of nitrogen creep across a landscape lit by the memory of a sun that can no longer warm anything, where the sky rains organic molecules synthesized from methane by starlight, where the atmosphere is slowly escaping into space and landing on the face of a moon that hangs motionless in the sky, locked in a gravitational embrace so tight that both worlds always show each other the same face, forever, where the volcanoes erupt, not magma, but slurry of water, ice, and ammonia that freezes before it finishes flowing, where the dunes are made of methane sand, and the wind that builds them comes from the breathing of a nitrogen ice sheet larger than France. Nothing about this environment corresponds to any human experience of the physical world. There is no frame of reference. There is no analogy that does not break under the weight of the differences. And that absence of analogy is, in a sense, the deepest source of Pluto's unsettling power. Human beings are comfort-seeking creatures. We navigate the world by pattern recognition, by comparing new experiences to old ones, by finding the familiar inside the unfamiliar. Pluto defeats that process. It offers no handholds. The surface is not like any surface you have walked on. The sky is not like any sky you have looked up at. The light is not like any light you have seen by. The cold is not like any cold you have felt. The silence is not like any silence you have heard. The isolation is not like any isolation you have endured. Each of these statements is not poetic exaggeration. Each is a precise description of a physical condition that has no terrestrial counterpart. Pluto is, in the most literal sense available to the English language, alien. Not alien as in foreign, not alien as in unfamiliar, alien as in belonging to a category of experience that the human nervous system was never designed to process. That is why Pluto's terror is not the terror of violence. It is not the kind of danger that announces itself with heat or noise or force. It is the terror of standing at the edge of comprehension, on a surface that should not be active but is, under a sky that should not be blue but is, in a cold so deep it turns common gases to stone, at a distance so vast that the sun itself cannot help you. It is the terror of a world that does not care whether you understand it, that does not conform to your expectations. That is not dead, not simple, not safe, not cute, and not anything you were taught it was. Pluto's atmosphere confirmed this in the most precise terms science can offer. The haze that controls its energy balance uses a mechanism unique in the solar system. The molecules leaking from its sky to its moon represent a process observed nowhere else among any known pair of worlds. The seasonal cycle that may cause its atmosphere to collapse and reform over centuries operates on a time scale that dwarfs any human institution. And the air itself, if you can call it that, is a poisonous trace of frozen gases so thin that it might as well not exist for the purposes of any biological function a human body performs. This is the environment. These are the conditions. And what makes them not merely inhospitable, but genuinely, deeply, psychologically terrifying is the combination. Not any single factor in isolation, but the way they layer together into a portrait of a world that is comprehensively, systematically, and irrevocably hostile to everything a human being needs to survive, to think, to feel safe, and to make sense of where they are. Pluto does not attack you. It does not burn you or crush you or poison you in any dramatic fashion. It simply does not include you. It operates according to its own physics, its own chemistry, its own cycles, and its own relationship with the distant star it orbits, and none of those operations have any accommodation for the biological needs, psychological expectations, or survival requirements of a warm-blooded, oxygen-breathing creature from the third planet. You would not die on Pluto the way you would die on any of the hostile worlds closer to the Sun. You would not die in fire, or under pressure, or in a blast of radiation. You would die in silence, in twilight, in cold so complete that your body would become part of the landscape, frozen into the nitrogen ice, preserved for millions of years under a sky that does not know you were there. That image is not designed to frighten for the sake of it. It is designed to communicate, as precisely as language allows, what kind of world Pluto actually is once you strip away the sentimental picture and look at the data. It is a world of extraordinary scientific interest. It is a world that has rewritten the rules of what small, distant, cold bodies can do and be. And it is a world that, for all its beauty and complexity, represents one of the most profound mismatches between human intuition and physical reality anywhere in the solar system. The atmosphere of Pluto does not protect you, it haunts you. It glows faintly blue in a sky that is otherwise void. It rains organic chemicals onto a landscape of frozen gas. It bleeds slowly into space and lands on the face of a moon that stares back at you, unblinking, from a fixed point in the black sky overhead. It is beautiful in the way that something can be beautiful and completely inhuman at the same time, and it is not even the strangest thing about where Pluto sits, because Pluto is not floating alone in empty space. It is the largest known resident of a region that is itself one of the least understood and most quietly terrifying frontiers in the solar system. Pluto is the threshold. It is the door. And what lies beyond that door, and what Pluto's existence at its edge tells us about the solar system we thought we knew, is the final piece of this story. Pluto does not orbit the Sun alone. It never has. From the moment of its formation, or more precisely, from the moment of the collision that shaped it into the world we observe today, Pluto has been locked in a relationship with another body so tightly bound and so mutually defining that calling Charon simply a moon misses something fundamental about what the two of them are. Charon is not a small rock circling a larger one the way most moons circle most planets. Charon is enormous relative to Pluto. Its diameter is roughly 753 miles, which is more than half of Pluto's own diameter of 1,473 miles. Its mass is roughly 1/8 of Pluto's. The ratio between them is closer than any other known planet-moon pair in the solar system. For comparison, Earth's moon has a diameter roughly 1/4 that of Earth, and a mass roughly 1/80th that of Earth. The Pluto-Charon system is something different. It is a binary. Two worlds orbiting a common center of gravity that lies not inside Pluto, as it does for Earth and its moon, but in the empty space between them. They orbit each other, face to face, locked in what scientists call mutual tidal locking. Every other tidally locked moon in the solar system, including Earth's moon, shows the same face to its planet, but the planet does not return the favor. The planet rotates freely while the moon is locked. Pluto and Charon are both locked. Pluto always shows the same face to Charon. Charon always shows the same face to Pluto. They rotate in perfect synchrony, each one's day exactly equal to their mutual orbital period of 6.4 Earth days. If you stood on the Charon-facing hemisphere of Pluto, Charon would hang motionless in your sky. It would never rise, it would never set, it would never move. A large, grey, cratered world hovering at a fixed point above the horizon, roughly 7 times the apparent diameter of the full moon as seen from Earth. It would be there when you looked up in the morning. It would be there when you looked up at night. It would be there next week, and next year, and next century. The two worlds are frozen in a mutual gaze that has persisted for billions of years and will persist for billions more. The 2025 study, led by Adine Denton at the University of Arizona, shed new light on how this extraordinary configuration came to be. The prevailing model for the formation of the Pluto-Charon system had been a giant impact hypothesis similar to the one that explains Earth's moon. A large body struck Proto-Pluto. The collision partially melted and deformed both objects, and the debris coalesced into Charon. The model worked well for Earth and the Moon, where the energies involved were high enough to treat the colliding bodies as essentially fluid. But Denton's team demonstrated that applying the same fluid body assumption to Pluto and Charon was a mistake. Pluto and its impactor were smaller, colder, and composed primarily of rock and ice with real structural strength. When the team ran impact simulations that accounted for the material strength of these bodies, rather than treating them as formless fluids, they found something no one had predicted. The two objects collided, stuck together in a temporarily stable snowman-shaped configuration, rotated as a single elongated body for several hours, and then separated while remaining gravitationally bound. Kiss and capture. Not a violent explosion of debris that gradually reassembled. A slow-motion collision between two rigid, icy worlds that touched, held, and then let go, without ever losing track of each other. The researchers noted that the specific parameters that successfully reproduced the capture also placed Charon in an orbit consistent with the one we observe today. The model was not just plausible, it was precise. The heat generated by that collision, combined with the tidal forces during the hours when the two bodies were joined, and during the subsequent orbital circularization, contributed to the thermal budget that has sustained Pluto's geological activity over the ages since. The kiss and capture event did not just create Charon. It helped set the conditions for everything New Horizons would discover 4.5 billion years later. The mountains, the glaciers, the convection cells, the cryovolcanoes, the possible subsurface ocean, all of it traces back, at least in part, to a gentle catastrophe in the ancient Kuiper Belt, where two icy worlds collided just slowly enough to stay together and just violently enough to change each other forever. Pluto has 4 other moons besides Charon. Nix, Hydra, Kerberos, and Styx are small, irregularly shaped bodies ranging from roughly 6 to 30 miles across. They orbit farther out, beyond Charon, in a complex gravitational dance that is influenced by the binary nature of the Pluto-Charon system. Their orbits are nearly circular and nearly coplanar, which suggests they formed from the same debris disk that was created during the collision that produced Charon. They are tumbling chaotically, their rotations unstable and unpredictable because the gravitational field they orbit in is not dominated by a single central mass, but by two masses orbiting each other. For a small moon orbiting a binary system, the gravitational environment is constantly shifting. The pull comes from two directions that change their relative positions on a 6.4-day cycle. The result is a rotational state that is, by the standards of orbital mechanics, essentially random. These moons do not spin in the orderly way that most solar system moons do. They tumble, they roll. Their poles wander. The sky from the surface of Nix or Hydra would not have a fixed set of stars overhead. The entire celestial sphere would precess and shift in a pattern too complex to predict without a computer. It is a small detail, but it adds to the portrait of the Pluto system as a place where even the things you might expect to be stable, the rotation of a moon, the fixed pattern of stars in the sky, are not. Now, pull back further, because Pluto does not exist in isolation even from the perspective of the broader solar system. Pluto is the largest known object in the Kuiper Belt, a vast region of space extending from roughly the orbit of Neptune at 30 astronomical units from the Sun to approximately 50 astronomical units, and in some definitions much farther. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. The Kuiper Belt begins at approximately 2.8 billion miles from the Sun and extends to at least 4.6 billion miles. It is not a belt in the neat, well-defined sense that the asteroid belt between Mars and Jupiter is sometimes depicted. It is a thick, diffuse, three-dimensional donut of icy bodies orbiting the Sun in a region so distant and so dimly lit that most of its residents have never been directly observed. The population of the Kuiper Belt is estimated to include hundreds of thousands of objects larger than 60 miles across and potentially trillions of smaller ones. Among the known objects are several that rival or approach Pluto in size. Eris, discovered in 2005, is slightly more massive than Pluto but marginally smaller in diameter, and its discovery was the direct trigger for the 2006 reclassification debate. Makemake and Haumea are also large enough to be classified as dwarf planets, and in 2025, the announcement of a newly discovered trans-Neptunian object, designated 2017-200-1, added another member to the growing census of large outer solar system bodies. This object, estimated at roughly 700 kilometers in diameter, or about a third of Pluto's size, occupies an extreme orbit that brings it close enough to be detected only about 1% of the time. Its discoverers noted that the existence of a single object on such an orbit implies that 100 or more similar bodies may exist at distances too great to be detected with current technology. That implication matters. The outer solar system is not the empty wasteland that the classroom diagram suggests. Beyond Neptune, the solar system does not end. It continues, populated by a vast, largely uncatalogued collection of icy worlds that have been orbiting in the cold and dark for billions of years. Some of them may be geologically active. Some of them may have subsurface oceans. Some of them may have atmospheres, at least periodically, maintained by the same volatile cycling that drives Pluto's atmospheric system. Recent James Webb Space Telescope observations of several other Kuiper Belt dwarf planets, including Eris, Makemake, Quaoar, Gong, and Sedna, have detected surface compositions that suggest internal processing and possible cryovolcanic replenishment of surface methane. The detection of specific isotopic ratios on Eris and Makemake indicated that both worlds are actively resupplying methane to their surfaces, possibly through cryovolcanic processes driven by subsurface liquid reservoirs. These are not confirmed oceans. The evidence is indirect, and the interpretations are still being debated. But the direction of the evidence is consistent. The outer solar system is not dead. It is not empty. And the processes that make Pluto strange and active are not unique to Pluto. They may be widespread among an entire population of worlds that we have barely begun to explore. Pluto, in this context, is not an endpoint. It is an introduction. It is the first world in this remote population that a spacecraft has visited with instruments capable of revealing what these bodies actually look like up close. And the lesson it delivered was unambiguous. The assumptions were wrong. The expectation of simplicity was wrong. The belief that distance from the sun necessarily means geological death was wrong. The conviction that small, icy worlds in the outer solar system are inert, frozen relics, interesting mainly for what they can tell us about the primordial conditions of the early solar system, was wrong. Pluto is not a museum piece. It is a living world, active and complex and strange, and it belongs to a population that may contain thousands of similarly complex worlds, each one unique, each one shaped by its own specific combination of size, composition, orbital history, and thermal evolution. This is where the emotional and psychological power of Pluto converges with the scientific story. Because what Pluto represents, once you have absorbed the geology, the atmosphere, the environment, and the context, is a threshold. It is the point where the solar system, as most people understand, it ends, and the solar system as it actually exists begins. The inner solar system, Mercury through Mars, is governed by the Sun in an obvious, dominant way. The Sun heats those worlds. It drives their weather. It shapes their surfaces. Its light fills their skies. The outer planets, Jupiter through Neptune, are farther from the Sun, but still clearly part of a system organized around it. Their atmospheres are heated by both internal energy and solar input. Their moons are influenced by the Sun's light, even as tidal forces dominate their geology. Neptune, the last of the giant planets, orbits at roughly 30 astronomical units. Sunlight there is 1/900th as intense as on Earth. It is dim, but it is still there. You would still know, standing on Triton, that the Sun is the most important object in your sky. Beyond Neptune, that changes. Pluto orbits at an average of roughly 39 astronomical units. At its farthest point, nearly 50. The sunlight at Pluto's average distance has already dropped by a factor of more than 1,500 from what reaches Earth. At its most distant point, barely 1/2400th. This is not a gradual transition, it is a cliff. The Sun's influence does not fade smoothly as you move outward through the solar system. It holds through the realm of the giant planets and then drops away with devastating speed as you enter the Kuiper belt. Pluto sits right at that transition. It is the first major world you encounter after crossing the line where the Sun stops being a sun and starts being a star. And that transition carries a weight that is not purely astronomical. It is psychological. It is existential. It changes what it feels like to be somewhere. Every world in the inner solar system, no matter how hostile, exists in a relationship with the Sun that a human being can instinctively understand. The Sun is up there. It is warm. It is bright. It is the center of things. It defines where you are and how you are oriented. You may be on a world that will kill you in seconds, but you are still in the Sun's neighborhood. You are still within the sphere of influence that anchors human spatial intuition. You are not lost. You are somewhere. Pluto is the first world where that anchor breaks. The Sun is visible, but it does not feel like the Sun. It does not warm you. It does not light your world in any way that resembles day. It hangs in the sky like the brightest star you have ever seen, and nothing more. Your relationship with it is optical, not thermal. You can see it. You cannot benefit from it. The psychological architecture of being on a planet, the deep unconscious assumption that there is a center, a source, a dominant presence overhead that organizes the world, is gone. You are not in the Sun's neighborhood anymore. You are in the outer dark. And the outer dark extends not for a few million miles, but for trillions of miles in every direction, continuing outward through the scattered disk and the Oort cloud, and then into the interstellar medium, the space between stars, where the sun is truly just another point of light among hundreds of billions, and the concept of a solar system has no meaning at all, Pluto is the doorstep of that void. It is the last place where you can look back and see the sun as something distinguishable from the general background of stars. It is the last place where the word orbit still means something tangible, where you are still gravitationally bound to the star that birthed the system you grew up in. Beyond Pluto, beyond the Kuiper belt, the gravitational tether thins and eventually breaks. Objects in the far outer reaches of the solar system are so loosely bound to the sun that a passing star can steal them. The Oort cloud, the hypothetical spherical shell of icy bodies that may extend a full light year from the sun, is the last frontier. Its members orbit so slowly that a single trip around the sun takes millions of years. They exist in a state of gravitational uncertainty, belonging to the solar system in principle but connected to it by the thinnest possible thread. Pluto does not live in the Oort cloud. It is much closer, much more securely bound to the sun, but it shares something with those distant objects that no inner planet shares. It exists in a region where the sun's authority is nominal rather than practical. The sun claims Pluto gravitationally, but it does not govern it thermally, energetically, or in any way that a human standing on its surface would recognize as solar influence. The world operates on its own terms, driven by its own internal heat, shaped by its own chemistry, cycling through its own atmospheric rhythms on its own 248-year clock. The sun is a distant bureaucrat that owns the title to Pluto's orbit but has no operational presence on the ground. This is the context that makes Pluto terrifying in a way that is different from every other world in the solar system. It is not the most violent world. It is not the hottest, the coldest in absolute terms, the most irradiated, or the most gravitationally crushing. It is the most remote. It is the most alien. And it is the most disorienting, because it is the first place where the framework that human beings use to understand where they are in space, the framework organized around a warm, bright, dominant star, stops working. Every other kind of planetary terror is, at its root, a terror of excess. Too much heat, too much pressure, too much radiation, too much gravity. These are terrors that operate within the system. They are the solar system being hostile in ways that still reference the sun's power, either directly or through the dynamics it creates. Pluto's terror is the terror of absence. Not enough light, not enough warmth, not enough atmospheric pressure, not enough gravity, not enough proximity to anything familiar. It is a world defined by what is missing, and what is missing is everything that a human being uses to feel oriented, safe, and connected to the cosmos they inhabit. And yet, the cruelest detail of all is that Pluto is not simple. If it were a dead, cratered, featureless ball of ice, the terror would be clean. You would look at it and see nothing, and the nothing would be the whole story. But Pluto is not nothing. It is an intricate, active, geologically rich world with a surface that records processes spanning billions of years and timescales as recent as hundreds of thousands. It has mountains and glaciers and volcanoes and dunes and an atmosphere with blue hazes and organic chemistry. It has a beating nitrogen heart that drives its climate and its winds. It may have a liquid ocean hidden beneath its frozen shell. It has a binary companion that it shares its atmosphere with, molecule by molecule, across the gulf of space between them. It has everything. Everything except warmth, everything except light. Everything except proximity to the star that made it. That combination, complexity without warmth, activity without energy, life without light, is what makes Pluto not just strange, but existentially unsettling in a way that purely hostile worlds are not. Venus is a nightmare, but it is a nightmare you can understand. Jupiter is lethal, but its lethality operates through familiar physics turned up to extremes you can at least picture. Pluto is something different. It is a world that should be dead and is not. A world that should be simple and is not. A world that has no right to be as interesting as it is, given where it is and what it is made of and how little energy it receives. And that wrongness, that defiance of expectation, is what makes it feel less like a planet and more like a message. A reminder that the universe does not organize itself for human comprehension. That complexity does not require warmth. That activity does not require sunlight. That the most profound strangeness in the solar system is not found in the roaring storms of the gas giants or the furnaces of the inner planets, but in the quiet, frozen, dimly lit margins where the sun's writ runs thin and the rules change without anyone noticing. Pluto changed the way scientists think about the outer solar system. Before New Horizons, the Kuiper Belt was an abstraction, a population of icy objects inferred from orbital dynamics and catalogued by distant telescopes as moving points of light. After New Horizons, it became a place, a region of real worlds with real geology, real atmospheres, real internal heat, and real complexity. Pluto was the proof of concept, the demonstration that even at the edge of everything, even at the boundary where the sun's influence fades to nearly nothing, the universe is still doing interesting things, still building mountains, still flowing glaciers, still cycling atmospheres, still erupting volcanoes made of ice, still producing landscapes that have no analogue anywhere else in the explored cosmos. The solar system does not end at Neptune. It does not end at Pluto. It continues outward into a vast, cold, largely unknown frontier populated by thousands of worlds that may be just as complex and just as strange as the one New Horizons photographed in 2015. The James Webb Space Telescope is beginning to reveal the surface compositions of some of those worlds, and the early results suggest that Pluto's activity is not an anomaly. It may be the norm for a class of objects that humanity has barely begun to study, and Pluto sits at the entrance to that frontier like a sentinel, the first face of the outer dark that was ever seen clearly. The first proof that the edge of the solar system is not a void but a wilderness, a frozen, dimly lit, almost incomprehensibly distant wilderness where the chemistry of the surfaces is written in ices that would be gases in any environment a human could survive, where the geology is driven by heat sources so feeble they were not expected to exist, and where the sheer distance from home imposes a silence, a darkness, and an isolation that goes beyond the physical and into something that might fairly be called spiritual. Pluto is terrifying, not because it will kill you quickly or dramatically, not because it is loud or violent or explosive. Pluto is terrifying because it is the most honest expression of what the outer solar system actually is: cold, dark, distant, quiet. Complex in ways that do not accommodate human intuition, active in ways that defy expectation, beautiful in ways that have nothing to do with comfort, and vast, so unimaginably, incomprehensibly vast, that the distance between you and the nearest help, the nearest warmth, the nearest familiar sky, is a number so large it stops meaning anything and becomes instead a feeling, the feeling of standing at the edge of sunlight, the edge of the known, the edge of everything that was supposed to end in emptiness but did not. What ended in emptiness was the old picture, the poster on the classroom wall, the 9 colored circles in a neat row, the friendly little snowball at the end of the diagram. That Pluto is gone. It was replaced by a real world, photographed in real light, measured by real instruments, and found to be one of the most extraordinary, most unsettling, and most profoundly alien places that human eyes have ever seen. The solar system does not end with a whimper. It ends with a world that has glaciers of frozen nitrogen, mountains of water ice, harder than granite, volcanoes that erupt slurries of ammonia and water, dunes of methane sand, an atmosphere that rains organic haze onto a landscape of frozen gas, and a moon that stares down from a fixed point in the sky, wearing a dark crown of molecules stolen from its companion's bleeding air. It ends with Pluto, and beyond Pluto, the darkness continues, populated by worlds we have not yet named, governed by processes we have not yet understood, stretching outward toward the stars in a silence so deep and so cold that the only honest response is not fear, not wonder, not excitement, but something quieter than all of them. The simple, humbling recognition that we are standing at the edge of what we know and looking out at something far larger, far older, and far stranger than the maps ever showed us. The maps drew a line and called it the end. Pluto proved it was only the beginning.